Bismillahirrahmanirrahim. Assalamu alaikum everybody. Today we are going to talk about another session, uh, data management and analysis for TM351. This session will covers part 16. I'm talking about scaling out, replication, and sharding. I just remind you to study the previous session, which was talking about scaling in and scaling out. And for this one, we are focusing on scaling out and the two important techniques related to which are replication and sharding. So we say that we have two techniques for scaling out databases to take advantage of multiple servers. The first one is replication technique, which increase the flexibility and availability of data, how copies of the data sets or database are placed on different servers so that it remains available in the event of server or network failure. So we have more than one copy. If one copy is failed, then we can go for the other one. The second technique is sharding, which increase the capacity of the database by splitting the database over several servers. Okay, so this is the base of scaling out. We said last time that we need to have small servers, many servers. Okay, now sharding is splitting or the sharding technique talk about splitting the data set over several servers, with each server then responsible for storing, updating, or any thing to do with any request from the client. The best is to combine these two techniques together. So in the next slides, we are going to talk more about each of them. So replication can also improve performance. How? Different clients can use separate servers for their data processing tasks. So this will improve the performance instead of just waiting many tasks in a pool to finish their requests on one machine or one server. No, in this case we have many servers, then we distribute our request between different servers so the things will be faster. Clients may prefer to use servers that are under less load or that have better network connection to the client. So this is also important and is responsible of increasing the performance. Okay, sharding and performance. Each server in the cluster takes responsibility for a segment. Now the segment is a shard because we have servers, we store part of the database, for example, or segment of the database or a data set, which we call it now shard. Okay, on the on these servers. Okay. So these segments of the data sets and deals with all the CRUD operations for that segment. So any segment on any server is able to be accessed using different operations like see, create, or read, or update, or delete operations, CRUD. The database would be sharded across servers for reasons of capacity and performance, as we mentioned before, with each sharded server also replicated to protect the database against failure. Also, we mentioned about this before. If one copy is failed for any reason, we still go for the other one. With many small servers within a single data center, which has many servers, server failure is expected and will be common also, as also we mentioned in last session. Okay, we said if we have for scaling out, we are using many servers, and this will increase the possibility of a server failure. Simplest to understand the replication is using master-slave based full replication with a single master. So we have one master, our single master, and we have many slaves. Okay, so it is master slaves. The database is replicated across several machines, with each machine having a full copy of a data set. This is shown in figure 16.1 that we'll see after a while. Once an update is completed on the master, the changes are then propagated to all other slave servers. So starting from the master and then propagated to the slaves. The replica set can be configured so that changes go directly from the master to slave, or even slave can pass the changes to another slave, as shown here. So we have two data centers. So this first data center has two computers or two servers, let's say. Okay, so we have one. For the other one, we have the center 2 also have this 1, 2, 3. So you can see that the primary computer is here. Okay, this is the master or primary, and those are slaves computers. Okay, those are slaves. So the client is here. Okay, the client send request to the master, and the master can connect with any of these slaves to send the request to one of them, and then the slave will complete the action and then send back the result, the updates maybe, or the writes to the primary, which send it back to the client. Also, one slave can propagate, sorry, I can see here. Okay, one slave can also connect to another slave, as we can see here. Okay, okay. If one machine fails, the data can still be found on other servers. This is the main idea of replication. When a failed member of the replica set is restored alive again, it will update its copy of the database with the transaction that occurred during its absence. Because we need all of the servers to have the same state of the dataset or database. If a new server is added, it will copy a database from the master directly. Okay, we have problem. How writes to different servers are coordinated. The solution is to use single master multiple slave approach, which Mongo database supports. Okay, now next we are going to talk about this single master multiple slave approach. Mongo database call these primary and secondary servers. Okay, with Mongo database, connection to the replica set must only through the primary server. I'm a client, I want any request, I should go to the primary server first. Then the primary server send my request to the suitable server or slave. A self-discovery process ensures that if a client connects to a secondary, it will redirect the client to the primary, because the client doesn't know which is the primary. So the client may send its request to any computer. So if that computer or server is not the primary, that server will redirect the request to the primary first, and then the primary take the action. Mongo database replica set okay. Mongo database replica set elect their own primaries, so client can't know which is the primary before they connect. This is what I said, that the client sent to any server, and then that server, which is could be slave, redirect the request to the primary. Writes are sent to the primary, but secondaries can accept notice of changes from other secondaries. Okay, and then finally, the replica set can be configured so that clients can read from the secondary servers. So this is based on the configuration we do. Okay, dealing with failures. Failures of the secondary server are handled straightforward. We don't have any problem if one of the secondary server is down or failure, because we can redirect the job or the request to another one. So the primary will continue to handle updates and propagate them to the remaining secondaries. Any client that were reading from that secondary switch to a different one, which will contain the same data, so we don't have any problem in that. When the first secondary recovers or reconnect to the replica set again, it can catch up with any changes it missed during its failure. Ideally, this recovery process is automated and unseen by both users and database administrators. So it is all done through the Mongo database itself. More complicated when the primary server fails. This is the problem actually, because we said that any request should go first to the primary. If the primary is down, then the whole system will be failed. Then we need to find solution for that. The solution is that one of the secondaries will take over the advantage of the failed primary. Okay, and this is called failover. So which secondary will take this opportunity to be the primary in this case? So there is an election between all the secondaries, and they will choose one of them to be the primary. Once the original or the previous primary, which is down now, alive again, it will connect to the replica set as a secondary. It could be primary again if again a new failure happened to the current primary, and the other secondaries elect that previously primary server again to be primary after the election. Database management system and Mongo database ensure resilience by replicating the database across several servers, either in different physical locations. It is important to talk about different physical locations. No meaning to put all the copies in one place. If a fire happened in that place, everything will go damaged, okay, or failed down. So it is better to put those copies in different physical places. Replication can offer small improvement of performance. For this, we should go to another technique, which is sharding, and see how it will help in that, how it will improve the performance, how it will be part with the new technology that mix between this replication and sharding. So we mentioned something about sharding, and now we go for more details. So it is powerful scaling out technique that handle large data sets or databases. The data set is split into a number of chunks, or we said segments previously, and the chunks or these segments are distributed across a number of shard servers. So we also can call them shards, segments or chunks or shard. Together, the shard servers make the shard cluster. As a database grows, more shards can be added, distributed evenly, possibly across extra machines. Okay, this is normal. So if my database becoming big, so I may add another server and store another shard on that server. So generally, a shard cluster is managed by shard controller instance. So this is the core of sharding technique, the controller instance. All clients deal with a controller directly. I cannot go to any server directly. I should go to the controller first. The controller intercept any query or update request and passes them to the relevant shard server or servers. The controller is also responsible for combining any responses from shard servers and returning the combined response to the client, as we will see in figure 16.2. Okay, this is our figure now. We have the controller in the middle, and we have the sharded on the top, 3 shard servers, and we have the config server. Okay, config server, and then we have the clients here. Okay, so we want to explain this figure and the contents of this figure. So Mongo database split the controller, the controller rules split it into 2 parts. A Mongo's, okay, simply passes requests and responses to and from the appropriate shard servers. It does not store any data or metadata itself. It's just take the request from the client and then send it to the suitable shard. How to know the suitable shard? It should connect to the config server that we just showed you in the figure. So this is the second part, which is the configuration server, another Mongo server that has information about these servers, what sharded exists in each server, what data exists in each shard, and any other information or metadata that we can find in there. So we start from the controller, the client sent to the controller connect to the configuration server, get information where to send this request to which shard, and then that shard will complete the process and send the result back to the controller, which in turn send it back to the client. If any one of the shard servers goes down, a portion of the data goes with it. Definitely. If one of them, like the 3 shards that we saw in the figure, if one of them is down, then it will be down with also the data there. So we cannot proceed with our request. If a controller fails, this is the problem. Clients have no way of communicating with the shard servers directly, and even if they could, they would not know which shard server store the data they need. In either case, the database will stop functioning. A shard cluster can be made more resilient through replication. Mongo database allows the replication of, so we need to replicate the controller itself so that we have many copies of that. If one of the copies failed, then we still go for the other one. In this case, our system will always be alive. Also, shards, we may replicate shards instead of stopping my request or holding on my request because that shard is down. We go to the replicated shard, and also we can replicate the configuration server. So all that parts can be replicated. In this case, we can see that we have or we join the two techniques together, the sharding technique and the replication technique. Figure 16.3 will show this. So this is an explanation. Okay, I go directly to the figure to show you all these things. Okay, you can see here. Okay, it's better like that. Fine. Okay, we can see this is Mongo. Okay, so you see that we replicated. So we have two. If one of them fell, then we still use the other one. Okay, we go to the shard. Okay, before the shard, we go to the configuration. We go to the configuration server. This is the original one. Okay, then we replicated 1, 2. Okay, go to the shards. We have one shard replicated. We have this shard replicated. Okay, so everything is replicated. Now we have the client here, so it can access and send request and get its answer without any problem. The use of sharding can extend the size of a database without limit, definitely, because we said that we have many shards, we have many segments, the database becoming big, then we need more servers, more shards, even more replication for that. Okay, the last topic is about keeping processing near the data. Okay, we will have problem if I am a client and I want to process my request. I want data from server somewhere okay, away from me. Then I need to call that data, bring that data to my side, and then do the process and complete my request. Okay, this is fine, we can do that, but this will cost us very much. The process of getting this data from different faraway servers could have or make problems, jam, for example, hacking, make the process slow, and so many things. So the best is to send my request to the server there and complete my request there in the server, okay, in the shard, in the whatever, okay, place, and then send back the result to me. So this is the best way. So we do that using a technique called map reduce, which is a programming pattern for analyzing data. It involves two stages, map and reduce. The core idea is that Many data analysis tasks can be broken down into sub-programs or sub-problems. Actually, it is same as we do for programming languages. When we have big problem and then we distribute this to sub-problems and finish each uh, sub-problem by itself and then combine the result together. So it is the same. So here each sub-problem can be answered independently to produce partial answer. Then we combine these partial answers to get the requested answer. In database terms, map stage operates on each document or record in the database, deriving partial answers to a query. The reduce stage operates on the pool of partial answers, combining them into further partial answers. So we reduce, okay? So we distribute in the map stage and then we reduce them by getting the partial answers and combining them in the reduce stage. Figure 16.4 is an example, actually shows an example. So this examples requested the summation of the square of the numbers between 1 and 5. So the whole process will be as written here. The whole process will be like that. What happened? Okay, I think it's enough. You can see here. Okay, first of all, in the map process, we take the numbers from 1 to 5. As you can see, we have the numbers now. Those are the numbers 1 to 5. Then we square each number in this part. So square of 1 is 1, square of 2 is 4, square of 3 is 9, and so forth. Okay. After that, we start combine the result partially. Okay, you can see here. Now, actually, the process is clear. We square each value, then we do summation for the results. Now, this is partial result. This is 1 and 4. We do summation for 1 and 4. Then we get 5 here. So this is the first partial. And then we have here the second partial, 9 plus 16. Okay, then it is 25, and then again the result here with the result here. Okay, this is another partial, and then we take this okay, answer with this answer to get the final answer. Okay, so this is how we okay use this technique, map reduce technique. Another example shown in figure 16.5. Okay, also something about accident database and talking about victims. Okay, in short, we look at colors. You see, like for example here, okay, you see this, sorry, two colors, not okay, my finger is big. Okay, these two together, we combine them here. Okay, also we take this this color, for example, this blue with blue here together, then combined here. Okay, also we take these two here, combined together until we reach the final result here. So you can see that we have. For example, this one again, we have here 1 and here 2 count. Okay, then we combine them, so the count will be 3. So for this color we have also 2 here. Okay, where is it? This one. Okay, we have also 2 this part. So combine them together, we will get 5. Okay, the same thing. And that is all about chapter 16. Very fast we go to the conclusion. So this part discuss how to scale out a database using the 2 important techniques, replication technique and sharding techniques, as we discussed them previously. Uh, Scaling out can lead to performance increase, and this is a very important advantage. Sharding can increase performance also, as you can see also here, by allowing different servers to handle different requests, or allowing the servers to handle different parts of a large request, as also we mentioned before. And finally we conclude with the data behind MapReduce, which is to keep the process as close to the data as possible, thus reducing the need to move large amount of data across the network and the problems that facing this moving of data. And however, threading the data across multiple servers can lead to problems with old or inconsistent data, but we still can cope with these problems. That is everything about this session. Thank you very much and good luck.